Good morning. Hope you had a good long weekend-ish. Yesterday off. Doesn't affect us, but nice to have. Like I was saying, I'm like, I don't think I remember how to do this. We only had one day off. I don't know. Okay, so good morning. Good morning. Good morning. Let's see here. Was there anything I wanted to say? Oh, there was. Uh-oh. All right, there was something I wanted to say. What did I decide? Okay, so I was kind of fiddling around with the material, and usually I would wait until we've covered the next chapter as well, but I think we're going to see quite a bit more of this chapter that we're in right now than I usually do. So I decided that once we finish this chapter, we're going to have test one. Oh my gosh. And if all goes well, so my plan is today we're going to cover the binomial distribution. And then on Thursday, we're going to do kind of the other ones. We're not going to focus so much on them, but we need to be able to recognize them at least. And so then I'll cover kind of the other distributions that could come up. And then on Friday, I'm going to do kind of a test one review, tell you what's going on with the test, and hopefully I'll have a better idea. I'm still trying to decide if I need to watch you during the test or what, but anyways, more on that later this week. So test one is next Tuesday, so a week from now. Okay, so and it'll be during our class time, of course. So I'll write it in red. Warning. Test number one on Tuesday, October 19th, during class time. Okay. All the material that we've covered so far. Okay, and so you have quite a few assignments that you're working through, and they're all due on Friday. I'm going to post a couple more just so we can kind of stay on top of things here. I'll make them a little bit shorter this time because I know they're quite long. I know that. But it's good to have all that practice. So that's why I'm kind of overloading you on those first couple of chapters because they can be tricky, right? And so, okay, so in terms of review, right, we talked about the normal distribution. The normal distribution is the most common continuous distribution. Okay? And so the normal distribution is the most common continuous distribution. Okay. And we talked about all these different facts. How can we find areas under the curve, areas under the curve, areas under the curve are probabilities. Right, all those things. So how can we use the areas under the curve to find probabilities? And we looked at quite a few examples last day. And then I am pretty sure I left it at, okay, and then you can read about how do we evaluate if we have a normal distribution. So just to brush up on that, to evaluate whether we have a normal distribution or not, we can use what's called a QQ plot or what is it, a quantile plot? We just call it QQ. I don't remember what the Q's stand for. I think it's quantile. So to evaluate whether we have a normal distribution we can use a QQ plot. I'm just going to say QQ. We can use a QQ plot and look for, what do we look for? It maps the actual observations against the theoretical normal distribution. So if X equals Y, then you have a line on the diagonal, right? So we can use a QQ plot to look for a line, a straight line, I should say. Look for a straight line across the diagonal. Right. Good. So call it the end of the review. I did leave you guys to read that on your own, but it's not so bad. So if you missed that, then you can go back and brush up on it. But it's nothing crazy. So today, what I want to do is I want to focus on the binomial distribution. So the binomial distribution is, I would argue, the most common discrete distribution that we're going to deal with. So the binomial distribution I'm going to say is one of the most common discrete distributions. One of the most common, because I'm not going to put myself out there and say it's the most common, but it's one of the most common, common discrete distributions. So when we say discrete, what we mean is countable, right? And so you can have 0, 1, 2, 3, whereas here, when I said continuous distributions, remember, we're on a number line now, so you can have any value can happen, right? And so here, continuous is from -infinity to infinity in theory. And whereas a discrete distribution is 0, 1, 2, 3, and so on and so forth. Okay, so that would be the difference here. So the binomial distribution is kind of a fun one because we can calculate probabilities by ourselves. But in order to get there, we want to develop some, just some theory around it. So I've got the geometric distribution here. We're not covering it until next day. Okay, so we are covering it, but I want to focus on the binomial distribution first, because like I said, it is kind of the most common, and then I'll have those other distributions on Thursday that we'll talk about. Okay, so the binomial distribution is a situation. So here, I'll update this until Thursday. Okay, so the binomial situation is whenever you have a success failure, okay? So I'm gonna copy this and bring it into our notes here. Okay, so a binomial situation is when we only have two possible outcomes, right? Yes, no, success, failure, pass, fail, right? All of these are just variations of success, failure, right? And so the success will be whatever outcome we're interested in, right? So it's not necessarily positive. In fact, it's often quite negative, right? So if you're interested in, how many people die from a disease, then that would be considered a success. I know that that's kind of weird, right? But it's whatever you're interested in, whatever you're studying is going to be considered a success. So a success will be the outcome of interest. So that's kind of weird, right? But that's because we're interested in, how many people died, how many people got the disease, how many people, whatever. Okay, and so what you'll notice is that even if a situation isn't necessarily binomial to begin with, often we can reduce it to a success failure situation, right? So a lot of situations, I'll say this in light blue here. So many situations can be reduced to a binomial situation. So for example, right, if we're talking about maybe a categorical variable, because often we are talking about categorical variables in this case, because the numerical variables are going to be on a continuous scale, right? And so often. And so for a lot of these, we're going to be talking about categorical data. And so what if we talk about first year, second year, third year, fourth year? Let's consider that. So for example, if we have first year, second year, third year, and fourth year students, right? If we're interested in the number of first year students, right, what could we do? Well, if we're interested in here, this could be a success. And then if they're not in first year, then they would be considered a failure. Right? So then we could in theory separate the population into success, failure. Okay. Well, so we're not going to talk about, because these don't necessarily have even probabilities, so we can't go that far, but I mean, in theory, you could. Probably 0.25 to the power of 3, right? 4. But that's assuming that they have even probabilities, which isn't necessarily true. But that is a good segue into, okay, so what we're going to be talking about is a success, right? So great guess, perfect guess. So we're going to need some probability of a success, okay? And so what's really important to have a binomial situation is that each outcome must have a fixed probability, okay? Which is to say that the probabilities are independent, right? So it doesn't matter how many times you flip a coin, for example. Let's say flipping tails is a success and heads is a failure, right? Here we have this naturally occurring success failure situation. So we didn't need to do anything to construct that. But so you flip a coin, right? And every time you flip a coin, we assume that there's 0.5 probability of a tail and 0.5 probability of heads. And that's going to stay the same, right? And so the probabilities have to be independent. Okay? We're going to talk about the number of trials, okay? And so in n trials, we're going to see k successes. So that's the notation that we're going to use. And so in n trials, number of times you flip a coin, for example, I've got an example here, so I don't really want to go here, but maybe number of coin flips, for example. And then we're going to see K successes. So in that number of coin flips, how many tails did I see, right? And so number of tails, assuming tails is a success, right? So I've got this kind of a silly example because I personally do not shoot hoops. I'm terrible at all sports. And so to me, it's kind of funny, this example. But anyways, I'm shooting hoops. And I know the probability of each shot going in is 0.2. Okay. So, oh, is this the one that you were trying to answer? Probably. Now I see it. Way ahead. You gotta calm down. But it was a really good guess. Yeah. Pumped up. So okay, I see what happened. I'm 2 behind. Yeah, we're not going to do any Monte Carlo simulations here. So if I shoot this, yeah, not here, no. If I shoot this 3 times, right? So I'm shooting hoops and I shoot it 3 times, right? It can either go in or it doesn't. Okay, and we've established that each shot, the probability of each shot going in is 0.2. So what's the probability of exactly 1 shot going in? And so here I'm telling you to use S as a success. So S denotes a success or the shot going in or whatever. So what I want to show you is you already have the tools for solving this problem using a tree diagram. Okay, because each trial is going to be a layer of the tree. However, it quickly falls apart, even though there are only 2 possible outcomes at each layer of the tree, right? This gets out of hand really, really quickly. Okay, and so I want to solve it first using a tree diagram. Okay, and so this gets out of hand quickly. In theory, you could solve all binomial distribution problems using a tree diagram, but it's not very efficient, right? And so what we're going to see is, okay, how about we just use the binomial distribution? So there's going to be a formula for us to use. Okay, so first I want to solve it using a tree diagram. Okay. And I can't remember if in the notes that I posted, is there, no, I removed it because it wasn't showing up properly. So first, using a tree diagram. What's nice about the tree diagram is we've seen tree diagrams with conditional probabilities, but they still work for independent probabilities. And so what we're going to have is we're going to have kind of this first set of branches. Okay, so this is trial number 1. It can either go in or not, right? And so we said define a success or a shot going in as S. And then I'm going to have the complement of S. Okay. So this is trial number 1, or in this case, shot number 1. Okay. But in general, it would be trial number 1. So then, depending on what happened in the first trial, I shoot again. Okay, maybe it went in with a probability of 0.2, or maybe it didn't with a probability of 0.8. Right? Of course, each shot has to have a total probability of 1. And so, well, if it went in, I try again. I'm facing the same situation, right? Same set of branches, 0.2 and 0.8. So it can either go in or it doesn't. Probability stays the same regardless. So here, It either goes in or it doesn't, right? Saying that these, yeah, so yeah, there's going to be 8 combinations, and you can still handle it with a tree diagram, but you don't want to go with more than that. It gets really ugly. Yeah. Yeah, 10 times 1,024 combinations. I don't think you want to do that. That's terrible, right? And so I'm just showing you that you can do it with a tree diagram, but you don't want to. You're not going to want to, even after 3 shots. So here, this is trial number 2, or shot number 2 in terms of this problem. So then I go for shot number 3, and maybe what I'll do is I'm going to bump this over just a smidge because I didn't give myself very much room. I never do with these tree diagrams. Uh-oh, right? So you can see how quickly this gets out of hand. If we think about just 5 trials, right, then you would have to have 5 layers, and it's huge. We're just talking about 3 trials here. So trial number 3, or in terms of the question, shot number 3, same deal. It can either go in or not, in or not, in or not, in or not. And 0.2, 0.8, 0.2, 0.8. It's nice to put these probabilities at the end of each branch, right? You might feel lazy and not want to put them, but then it makes it harder to do these probabilities, right? So remember, the probability of ending up at the end of each branch, you just multiply down each of the branches, right? So to find the probabilities, and maybe I'll give myself a little bit more room here. To find the probabilities at the end of each branch, multiply down. Okay. So here, right, we're going to have a bunch of different combinations of 0.2 times 0.8. Right, and so if I have 0.2 times 0.2 times 0.2, right, that's 0.2 to the power of 3. That's going to be 3 shots going in a row. That's the only way that that can happen, right? All 3 shots going in. But then I could have, so what I like to do is, if I'm doing a tree diagram, I like to just put the different combinations at the end here. And I know that's technically, incorrect, but tree diagrams are just for us to solve the problem, right? And so here, S, S, not S, S, not S, 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 not S, not S. Maybe I should have used failure instead of not S. Too late now. Not S, 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 not S, S, not S, not S, not S, S, not S, not S, not S. Okay, and the probability of each of these happening, you can multiply down each of the branches. Let's go back to the problem that we're trying to solve here. And so if I shoot 3 times, right, so 3 trials, what's the probability of exactly 1 shot going in? Okay, that's going to happen in a number of different ways, right? Exactly 1 shot going in, if I kind of trace down these trees, if the first one went in, then I would have to make sure, if I only want exactly 1 shot, that can only happen if the first one went in and then the other 2 don't. So here, is one outcome where I have exactly one success, right? You could also look at these little shorthands, which is usually what I end up doing, and see, okay, here I have 3 successes, 2 successes, 2 successes. Here I have exactly 1. Okay, good. Here I have 2 successes. Here I have 1 success again, right? Or you can trace down the tree. It doesn't matter. But what you'll see is your other option is it doesn't go in at the first one. It goes in on the second one, but then it can't go in on the third one because we're only interested in 1 going in. What if it doesn't go in the first one, it doesn't go in the second one, then to satisfy the criteria that we want, it has to go in on the third one, right? And so what we see is there are 3 possible combinations where we have exactly 1 success, right? And so we see there are 3 combinations with exactly 1 success. Okay. So we need to take that into account. Each of these will have the same probability though, because we have 1 success with a probability of 0.2, and then we have 2 failures with a probability of 0.8. So it doesn't matter which order we have them in, right? We're going to see that if I copy down the first one, if I have the probability of a success, failure, failure, that's going to be 0.2 times 0.8 times 0.8, right? The probability of the next one, not S, S, not S, not S, S, not S. Well, that's going to be 0.8 times 0.2 times 0.8. Notice that these are the same calculations, right? And so the last one is going to be the same deal, not S, S. 0.8 times 0.8 times 0.2. Notice in each of these situations, you have 0.2 times 0.8 to the power of 2, right? 0.2 times 0.8 to the power of 2. Oops, sorry. There. 0.2 times 0.8 to the power of 2. Okay. This is the same as the probability of 1 success, right? Times the probability of failure to the power of however many failures, right? And so here, what I want you to notice this is going to be the probability of success to the power of, and I just want to show you, like I use the caret just to emphasize that it's to the power of the number of successes times the probability of failure to the power of the number of failures. Okay. And maybe I shouldn't say fails because it looks like tails and that might be confusing. Number of failures. Okay. But we also have 3 different combinations, right? And so we have 3 different combinations, 3 combinations. So, right, this is where the binomial distribution comes from. It takes the number of combinations and it just lets us calculate the number of possible combinations without the tree diagram. And then it takes the probability of success to the power of however many successes, and it takes the probability of failure to the power of however many failures. Okay, and so here, the binomial distribution does this calculation, right, without a tree diagram. The binomial distribution does this calculation without the need of a tree diagram, which is awesome, right? Because as you can imagine, right, we said, okay, what if you have to do 10 trials, right? What if I shoot this, shoot 10 times? Well, that's reasonable, right? That's a reasonable scenario to consider. But when it comes to making a tree diagram, it just gets out of hand, right? And so, so that's what I want to show you, right? I think I have it written down here. Okay. So here I've used the little apostrophe, so which is prime, S prime, and usually that's what I end up doing because I'm lazy, because I don't want to draw out the C. It doesn't matter, but for some reason I just, when I type it, it just becomes prime, but that's okay. And so, all right, good. Just wanted to see what was in the notes and what wasn't. So what we're going to find, let's actually find these probabilities. We can find the probability of at least, probability of, oh, not at least, of exactly one success is each of those probabilities added together. When we're adding is when we catch ourselves saying or, right? And so we multiply when we say and running down, so it has to be S and not S and not S, okay? Or, right, so whenever you're saying or, you're going to be adding, or not S, S, not S, right? And when I say not S, S, not S, really what I'm saying is not S and not S, or not S and not S and S, okay? And so it just kind of pay attention to when you're saying and when you're saying or, and that's going to help guide you to determine if you're going to be adding or if you're multiplying. But in general, you're going to be adding, or sorry, that'll throw you off. You're going to be multiplying down the branches to find the probability down the branches. And so what you're solving there is at least one, but we want exactly one, which is going to be a little bit different. Yeah. And so here, right, so you're going to be, yeah, it is tricky, and it's all in the wording, right? And so so that's probably the hardest part, is reading it and figuring out what you need to do. And so just remember, you're going to multiply down each of these branches, great, and then to figure out, okay, it can be either one of these branches, one of these three branches, then you're going to add those probabilities. So what you get is you get, I'm going to keep this on one page here. So the probability of S, not S, not S, plus the probability of not S, S, not S, plus the probability of not S, not S, S, which we decided was 3 possibilities of the same outcome, right? 0.2 to the power of 1, just to emphasize that that's one success. You don't need to have it to the power of 1, but I just want to show it because we're just establishing what's going on here. And 0.8 to the power of 2. So what do we get? We get, if I do 0.8 to the power of 2 first, and then I take it times 0.2 and then times 3, I get a total probability of 0.384. Yeah. So that's the probability of exactly 1s. Okay. So in comes the binomial distribution. It looks scary to begin with, but we're going to talk about how we already know what's going on there. Okay. And so let's see here. So I'm going to bring this in here. And it's spread across 2 pages. Let's see here. Okay. So in order to be able to deal with any number of trials, okay, we use the binomial distribution to calculate the probability of k successes in n trials. Okay. And so here, we're going to calculate the probability of k successes in n trials. So the formula is a little bit nasty when we first sit down and look at it, but then we're going to work through it and it's not so bad. Okay, so if x is the random binomial process, so in this previous case here, we were looking at x equal to 1. Okay, and so I want to draw that connection here. Here we're finding the probability that x equals 1, exactly 1 success. Because k is the number of successes, right? And so here in general, we can have x equal to k. Okay. And so this function, yeah, exactly. This function here is a little bit weird, right? N choose k, if you haven't seen it before, we're going to talk about it. But it's really just establishing how many possible ways could I have k successes, right? And so this calculates the number of ways we can have k successes in n trials. Right, so instead of looking at the tree diagram and counting, okay, I see I can have 3 different outcomes, right? Instead of having to do that, n choose k. So you read this as n choose k. It's down here. It's not a fraction. It's its own function. Okay, so n choose k just calculates the number of ways to get k successes in n trials. So I'm actually going to highlight that down here because I am jumping down there to explain it. And so here, n is the number of trials, right? Or I guess I could read the list. K is the number of successes, of course. We already established that. N is the number of trials. Okay, how many times did you try to get a success, right? And then k is the actual number of successes. P is the probability of success, and then 1 minus P, which I often shortcut to Q, is the probability of failure. So we could have written P to the power of K, which we already saw, right? It's the number of success, or the probability of a success to the power of the number of successes. And then 1 minus P, which is the probability of failure, right? To the power of however many failures, right? N minus k is going to be the number of failures. And here, 1 minus p is q, which is the probability of failure. Okay. Okay, so in our little baby example, because we wanted to be able to handle it with a tree diagram, so it has to be a small example. So in our example, we found that this value was 3, right? It's not a very good example because we're going to try to find in 3 trials the one success. So 3, choose 1. So here in this example, we want to find 3, choose 1, which we already decided was 3, right? Looking at our tree diagram. But we can check it on our calculator by using, usually there's going to be an NCR function, right, on your calculator. For example, on this one, this calculator, I can't tell if it's showing or not, but above the division symbol, there's an NCR button. And so that's going to be your choose function. Or what I'm going to do is I'll show you on Desmos, the Desmos calculator, where to find it, okay, because we need to be able to calculate it. I think it's in the functions. Where is it? Where is it? Here. I'm going to hold it down. Hopefully it highlights it a little bit. So NCR is down here. And so this one requires it in a different setup. So it has the NCR function and then in brackets, N, comma, K. Okay, so in this case, I go back to the numbers 3, and then the comma is over here. I'm highlighting it or trying to 3, comma 1, and then close that bracket, right? And so we get an answer of 3. That's a little bit boring, right? Because we already found that, right? We know that it's 3. It's confusing because we're doing 3, choose 1. Right, and so let's do another one. So figure out how to do it on your calculator. It's going to be really important that you're able to do these choose calculations on your calculator. I've got some examples to go through. Oh, maybe not yet. So we're going to use our calculator just to confirm these, but I also want to bring your attention to scientific notation. So especially when you do 100, yeah, so N is the number of trials and K is the number of successes. So if I tell you, okay, I tried to do something 10 times, and I was successful 4 of those times. How many times was I not successful? It would have to be 10 minus 4, right? And so that's why it's N minus K. I'll see if that helped. Let's see. Okay, awesome. So let's just try 10, choose 2. So if you just imagine a tree diagram here with 10 different layers, and you want to figure out how many ways can I have exactly 2 successes. You could start with 2 successes. That one's easy enough. But then you could have a success and then a failure and then a failure and then a success and then a failure, 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 right? There's going to be a lot. In fact, 45 different ways that can happen. Okay, so let's try this on our, I'm going to do it on the Desmos calculator so you can see it. So I'm going to keep it there, and I want the NCR. I'm going to go a little bit faster. 10, comma 2. Close the bracket. 45. There's only one way to have exactly all successes and similarly all failures, right? And so if I do NCR of 5, choose 5, there's one way that can happen. Okay. Yeah. And then let's try NCR 5, choose 0 successes. There's only one way. So if it's all successes, then there's only one way, because then you can only go down the outside of the branches, typically, depending on how you set up your branches. But usually we want to follow some method. And then on the opposite side is all failures, which is going to be 0 successes, right? And so there's only one way for all of them or none of them to happen, but it's everything in between that we're usually interested in. So if I try 100, choose 45, okay, let's do 100, choose 45, and it does max out. Most calculators will max out at some point because there are just way too many combinations. 100, choose 5. Okay. So here it's giving me the actual number, 75,287,520. That's huge. But if I try it, oh, I didn't choose 5. It doesn't matter. I should have done choose 45. So let me try that again. 45. There. That's what I was looking for. So now notice that it gives me the scientific notation. But what I want you to do is try it on your calculator, because you need to be able to recognize scientific notation on your calculator. Easier said than done, because if I do 100, choose 45, this calculator, you can't see it, but it shows it the same way that I have here on the screen, okay? But some calculators just leave a little space and then it says 28, okay? And so you need to know how to use your calculator, or how to read your calculator rather. Sometimes it's very subtle, right? So one of the options here would be, it could write sometimes shown as, right? So something like this would be 6.14484728. Okay, that's subtle, right? So you have to be able to recognize when you have scientific notation. Okay, but being able to use that choose function is really handy, and it's just figuring out how many different combinations are there if I run down a tree. Okay, so then let's see, I think we have everything that we need to be able to solve some problems. Okay. So we can confirm our calculation. There's a typo here, should be 1. Sorry about that. So we can confirm our calculation with our tree diagram. So we already did, we found the probability there. Yeah, sorry, this is a typo. I should highlight it more. Should be 1. Little copy paste error, nothing to write home about. Okay, and so the probability that X is equal to 1 is 3, choose 1, which we already found was 3. That's pretty boring, but it matches our tree diagram, right? Of 3 different ways to get there. 0.2 is the probability of a success, right? To the power of 1 success, that's what we're interested in. And then 1 minus 0.2 is 0.8, so that's the probability of failure to the power of the number of failures, 3 minus 1. Notice that we end up at the same calculation that we had earlier, right? 3 times 0.2 times 0.8 to the power of 2, which puts us at 0.384. So this is, not surprisingly, the same result that we found using the tree diagram. All right. What's fun is that we can find the mean and the standard deviation of a binomial distribution. That feels weird, right? Especially because we said, okay, binomials, we can only have success failures. So what's going on here? Why am I able to find a mean and a standard deviation? It is assuming that we have a large number of trials, a large enough number of trials, and it is exactly an expectation or an expected value. So we can find the mean, and the mean is often called the expected value. Okay. The expected value of x, which we often denote as e of x. So the expected value of x, where x is some random variable. Now that random variable can follow many different distributions. We've seen the normal distribution, right? And we can talk about the binomial distribution. And then next day, I'm going to introduce you to the geometric distribution, the negative binomial, and the Poisson. Those are all just different distributions depending on the situation that you have, right? So for the binomial, the one we're focusing on mostly for this course, because it's kind of the most common, it counts what's the probability of an exact number of successes. Okay. So we can find the mean number of successes by taking n times p, right? So if I say I flip a coin 10 times, n is 10, we understand that if I flip a fair coin, let's assume all coins are fair, the probability of success is 0.5. So that's where you get the, okay, I would expect to see 5 successes, right, in 10 coin flips. So what you're already doing in your mind is you're taking 10 times the probability of success, right, P. So we already know how to do that. We just haven't set it up like a formula before, right? But we have a good understanding of what's going on here. The standard deviation, not so much, right? The standard deviation is going to be the square root of n times p times q. Notice here, right? Oops, go pink. Q is 1 minus p. So I tend to use q instead of 1 minus p because it makes it look a little bit cleaner and easier to read. Okay, and so I want you to really be aware of that when you see a q, it's just 1 minus p, or q is the probability of a failure. Oh, clean that up. Failure. Not so clean, but oh well. Okay, so we can find the mean and the standard deviation of some number of trials. Okay. Let's do an example. Whenever I do this example, I always jump the gun. And so I'm, okay, let's see here. I'm going to try to slow my horses here. So the S&P 500 index has a probability of 0.56 of increasing in any week. So what we're going to assume is that the change in the index in any given week is not influenced by whether it rose or fell in the previous week. That's a stretch, right? We understand that stocks are not independent week by week, but in this situation, we are assuming that. Okay? And maybe it depends on the stock that you're talking about. Maybe it's more reasonable for some than others. But so what we're going to do is we're going to let X be the number of weeks among the next 5 weeks in which the index rises. Okay. And so how many possible outcomes are there each week? Each week, it could either go up or it could go down, right? And so we have 2 possible outcomes. We are assuming that it's not going to stay steady, right? Or we could reformulate it as it either goes up or it doesn't, right? Meaning it went down or stayed the same. Okay, and so here for A, how many possible outcomes are there each week? So each week, it either increases or it doesn't. Okay, so here we have two possible outcomes. We have two possible outcomes, which lends itself to a binomial situation. Notice that if it doesn't, that's kind of covering two situations, right? It could stay the same or it could decrease. Stay the same or decrease. Okay. Now, let's see here. We're given the probability of 0.56 of increasing. So that's also good because we need for the binomial distribution, we're going to need the probability of success. But before we can do that, identify what a success is in this case. So in this case, a success is going to be if the index rises, right? So let X be the number of weeks among the next 5 weeks in which the index rises. So that's going to be a success. So B, a success is the index rising, right, or increasing. We can use, or I haven't actually read the whole question, but anyways, so here, what are N and P in this case? So N is the number of trials. How many times did you try to see this, this index rising? Well, we're going to talk about 5 weeks. Okay. P in this case has to be the probability of a success. And so that's given, right? The probability of success is 0.56. So N is 5, right? 5 weeks observed. And P is 0.56, the probability of an increase. Okay. So yeah, so Q would be 1 minus that 0.56, which is the 0.44. But we don't actually need to establish that. What we need is we just need the probability of success and the number of trials, and then we can calculate different probabilities based off of that. So first, we're going to establish what are the possible values of X. So X is the number of weeks among, right? It's established here. Let X be the number of weeks among the next 5 weeks in which the index rises. So that could be all 5 weeks, right? Or 4 weeks, or 3 weeks, or 2 weeks, or 1 week. Or the one that people always forget is that the index might not rise in any of the weeks. So 0 is also an option. Okay. And so here, what's the question? Possible values of X. X can be 0, 1, 2, 3, 4, or 5. Okay. Don't forget about the 0 option. That's really, really common. Yeah, for something long. Yeah, it's happening. No, it won't be so bad. It won't be so bad. Okay, so now let's use these this information. What's the probability of the index increasing in more than 3, not including 3 of the weeks? Okay, so more than 3. Okay. More than 3, not including 3, is either, well, we listed all our possible outcomes here is 0, 1, 2, 3, 4, 5. So the only times that it could be more than 3, not including 3, is if it rose in 4 weeks or 5 weeks. Notice how we're saying 4 or 5. Okay. 4 or 5 weeks. Okay. So then the probability that X is greater than 3, not including 3, is the probability that X equals 4 plus the probability that X equals 5. Okay, so here, and maybe I'll use a green. All right. Okay, so the first step is just establishing in terms of probability notation. What do I need to find? I want to find the probability that X, which is the number of successes, is greater than 3, not including 3. So my options here are, well, X could be 4 or X could be 5. So what I'm going to have to do is I'm going to have to calculate these probabilities individually and then add them together. Often I don't do it in the same row because it gets too big. So what I'm going to do is I'm going to, maybe what I'll do is I'll leave some room here to plug these values back in. Okay, but I'm going to do the calculation of the probability that X equals 4, and then I'm going to do the probability that X equals 5. Okay. So leaving some room, I'm going to find the probability that X equals 4. And you know what? Maybe I'll write out the general formula here, just so we can remember it. You probably don't have it memorized. I do, though. I use it, or I teach it so much that it just kind of sticks. So it's N choose K. And if you think about it, the formula just kind of makes sense. You don't need to memorize it, but it does make sense. So it's N choose K, P to the power of K times Q to the power of N minus K. Or 1 minus P to the N minus K, right? So, oh, I'm just, sorry. I'm just seeing the chat. So 1 minus less than 3 wouldn't quite get you there as quickly as doing it this way, but I think you probably caught on to that already. Okay, so in general, we have this formula here, and so I'm gonna just box that off because that's just our formula. And you can see that it's on the formula sheet that I posted. You're in charge of making your own formula sheet or kind of cheat sheets, so this should definitely be on there. So then the probability that X equals 4 in 5 trials is going to be 5 choose 4 times 0.56 to the power of 4 times 0.44, right? 1 minus 0.56 is 0.44. And maybe I'll highlight that here. 1 minus 0.56 is 0.44. To the power of, well, if I have 4 successes, then 1 must be a failure in a total of 5. Okay. You don't want to do any rounding here. So as little rounding as possible, because sometimes these values are going to be really, really, really small. And so you don't want to do any rounding. You want to keep all your decimal places. So first thing I'm going to do is I'm going to find 5 2's 4, and I get 5. There's 5 ways that can happen. And then 0.56 to the power of 4. Oops, if I can punch it into my calculator properly, there is 0.0983446 times 0.44 to the power of 1 is just itself. So keeping all those decimal places on my calculator, and I'm doing it on the side here, just so I'm not switching back and forth so much, times 0.44 times 5, I get 0.216358912. Keep as many decimal places as you can. Okay. Usually there's a store function, so many calculators have a store function, and so you can Google how to use a store function. So use the store function on your calculator. Okay. Well, so business math is different because money only goes to 2 decimal places. So, but for us, because these are probabilities, right, we need to keep as many decimal places as we can until the very end. And then it's kind of a judgment call of when you can round it. But yeah, business math, they're different because they're talking about money. So then you only have 2 decimal places. Okay, so what we can do now is we could put this value here, but I'm going to store it. So on my calculator, this kind of engineering one, there's a store button, and I think I just hit it and quit it. Store it, and then I have to pick a letter up top. So I did have to Google that, and you can just Google if you find some sort of store button on your calculator, it can do it. So STO is usually what it's called. Okay, so I've saved it. So what I could do is I can go back up here and I could say, okay, I'll write down my first one, but I'm actually going to use the stored values. Can only display so many decimal places, right? But 0.216358912 plus, and so this came from, oh, maybe not that like that. It came there. Oh, so on this calculator that I have is, I don't actually like this one so much. I've got a couple of ones, but this one is the one that I end up using often. So this is a Casio FX991EX. I think this is kind of a hard to find calculator, but any one of the engineering calculators are pretty good. They have a lot of different functions. So you can kind of play around. But usually if I'm on Amazon, then you can kind of zoom in on the buttons. And let's see here. I also have this one, the business calculator. And so, and it's got a store function. Yeah. You can usually zoom in, and usually it's called, and I'll show you on this one because it's kind of clearer to see, but there's the STO button. So usually on Amazon, I just kind of zoom in on all the buttons. And if I see an STO, then I know it can do it. Or you could just, you're safe. If you write out all the decimal places and plug them back in, that's fine too. just annoying. Okay, so we found the first part, the probability of exactly 4. So now we want to find the probability of exactly 5, because it could be 4 or 5, right? And so here, the probability that x equals 5, same setup here, is, and I'm not writing out the general formula, although I probably should, but I have it up here. So it's going to be 5 choose 5. 0.56 to the power of 5 times 0.44 to the power of 0. Anything to the power of 0 is 1, right? 5 choose 5, we just established there's only one way to have all successes, right? So this becomes a nice straightforward calculation exactly. And so we get 1 times 0.56 to the power of 5 times 1. Almost grabbed my other calculator. 0.56 to the power of 5 is 0.055073176. Times 1 is just itself, right? And so here plus 0.055073176. I'm going to add that to recall A. Good. So now I get a total probability of 0.2714320896 is my final probability. Got pretty messy here, but I think you get the idea. Right, this probability, how can I almost went to the wrong number there. This was a decoy, not this one, this one. Okay, good. So there are tips and tricks here that we can use, such as, well, if the total probability has to be 1, right? Sometimes it's going to be easier if we just find kind of we find the complement, right? The probability of the complement and subtract it from 1. That's going to be something that we'll see often. Okay, but for now, we've answered the question, right? More than 3, not including 3, 4, or 5 weeks. So the probability of that happening is 0.2714320896, right? I encourage you to keep all those decimal places, even now that we're done. There's no reason to round those at all. Okay, good. So what is the mean and standard deviation of this distribution? So the mean of this distribution I can't remember what F, maybe. The expected value of X, which is mu, which is n times P, nice, is going to be, my n is 5 and P is 0.56, which is probably what you would have gotten to if you just kind of sat down and I asked you, okay, on average, how many successes are you expecting to see? Well, I would expect to see 2.8 increases over 5 weeks. We understand that 2.8 can't happen exactly, but we're talking about over, in theory, an infinite number of 5-week intervals, right? How many successes would I see? I would see on average 2.8. So here, you don't do any rounding. This is just kind of, if you observed an infinite number of 5-week intervals, you would expect to see 2.8 successes. In terms of gambling here, would you bet on 2 or 3? Probably 3, right? 2.8, but and then n sigma is the square root of n times p times q, which is, and maybe I should bump these so you can see that they're different values. 5 times 0.56 times 0.44 that doesn't look very nice there. So then 5 times 0.56 times 0.44 just over here on the side, and then I square root that. Don't forget that square root. I have a standard deviation of 1.109954954. Okay. Good. So with a mean and a standard deviation, you might be tempted to say, well, if I have a mean and I have a standard deviation, couldn't I just use a normal distribution? And yes, you can. So, but it only works for a certain, for sample sizes or large number of trials, right? And so with a mean and a standard deviation, we can use the normal distribution, right? And so, but it has to satisfy certain criteria. We can use the normal distribution, and that's kind of weird. And I'll talk more about it next day because I know I'm kind of cutting it close here. We can use the normal distribution as long as n is large enough. So we're going to establish kind of how do we check that? Okay. And so before we go, right, consider what if we had to find the probability of at least one increase, right? At least 1 week with an increase. Find the probability that there is at least 1 increase in the 5 weeks, right? So at least 1, that's going to be 1, 2, 3, 4, or 5. You could do all of those, or we could leverage the fact that, well, the total probability has to be 1, right? So what if I just take away the one option where it doesn't happen, right? So if we look at, and that's why it's helpful to list all the possible outcomes here. At least 1 happens at 1, at least 1 happens at 2, at least 1 happens at 3, it happens at 4, it happens at 5. The only one where it doesn't happen is at 0. So what could we do? We could take 1 minus the probability that 0 increases happen, and then we're left with all these, right? Instead of adding up all these probabilities. So I'll leave you with that to try that, and that's where we'll start next day. And I'll also talk about the normal approximation to the binomial. But I'll leave you with that. If you have any questions, let me know. Otherwise, I'll see you on Thursday. Stop this here.